Good evening, everyone, and thank you for joining us to discover our universe with our lecture series from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, or as we call it, kipac. My name's Dan Wilkins, and I'm an astrophysicist at kipac, and I'm the coordinator of our public talk series. And we'll be live every 2 weeks with another one of these Discover Our Universe public talks. You can find out about our upcoming events on our website, kipac.stanford.edu/discover, or you can sign up to our mailing list. You can watch this or any of our past talks over on our website or on our YouTube channel. It's my great pleasure to introduce tonight's speaker, Dr. Jessie Muir. Jessie received her PhD in physics from the University of Michigan, and before that she completed her bachelor's at Michigan State University and received a master's from the University of Cambridge, where she studied as a Marshall Scholar. She was awarded a Porat Fellowship, which brought her to Stanford in 2018. Jessie's research focuses on measuring the properties of the universe on the largest scales to discover the properties of dark energy and to test our understanding of gravity and of fundamental physics. She works as part of the Dark Energy Survey, a collaboration of several hundred scientists around the globe to map the galaxies over a large part of the sky and to understand how they're distributed throughout our universe. And as part of her research, Jessie works on how to design experiments to protect them from the effects of unconscious bias of us scientists, and also how to communicate scientific concepts using cartoons. And we're delighted to have Jessie here with us tonight to tell us all about echoes of the early universe. Now, after Jessie's talk, we'll be hosting a live Q&A. So if you have any questions for Jessie, you can send them in all the way through the talk. If you're joining us on Zoom, head down to the bottom of the screen and click on the Q&A button, and you can send your questions in there. Or if you're joining us on YouTube, you can send your questions in on the chat. Alternatively, I'm going to put a link to a Google form in the chat on both Zoom and YouTube, where you can send your questions in. But for now, I'll hand over to Jessie.
Thanks very much, Dan. Thanks to everyone for tuning in. I'm going to share my slides now. All right, you should be able to see a title slide.
Yep, that looks good.
Great. All right, so I'm excited to be on here, talking to you all, while also talking to the wall in my living room. So as Dan said, I am currently a postdoctoral researcher at Stanford, and my research is in the field of cosmology. And cosmology is the field of physics, astrophysics, as the bio that Dan so kindly read kind of already described. It's the field that's concerned with the properties of the universe on very large scales, and what those large scales of the universe can tell us about fundamental physics. So the thing I find really compelling about cosmology is the way we tie together this understanding of fundamental physics to the large scale properties of the universe, and that relation goes both ways. We can use our knowledge of fundamental physics, so by that I mean our understanding of what everything's made of and what forces govern how those things interact and change over time. We can use theories of fundamental physics to build our understanding of what we're seeing when we look out at the universe. And then we can also use observations and measurements of the large scale universe to check the predictions of our theories and learn about the fundamental physics that they're trying to describe. So the main goal of my talk, I think, is to try and give you a bit of a flavor of how we try to approach this. And in the process, I'm going to do that through introducing something called the cosmic microwave background, which is a thing we can observe of the universe, which I'll tell you a lot more about in a couple of minutes, that I think is just also something very cool to learn about, which many people may not be familiar with. So before I get into all of that, I want to give a little bit of orientation to think about what kind of length scales I'm talking about when I'm saying large scales, and to frame how we think about how we're gathering information about the universe. So to start, I want to do a little bit of an exercise And I want everyone to imagine looking at the moon. So depending on your time zone and the orientation of your windows, there might be a few people who can actually conduct this experiment in real time. For the rest of us, we'll have to use our imagination. So what is happening when we look at the moon? There is light that initially came from the sun. It bounces off the surface of the moon and then travels through the space between the moon and us to reach our eye, or maybe the camera which took this picture that I am showing. And I'm talking through this because what I really want to emphasize is the fact that light travels at a finite speed. That is to say, it doesn't get from the moon to your eye instantaneously. It takes some time to travel through that space. And the phrase speed of light may be familiar to you. This may or may not be a new idea, that light takes time to travel. But I think it's really worth pausing and thinking about what that means when we're looking, especially at things that are very far away. So the light that travels from the moon to your eye takes about 1.2 seconds to get there. And that means when you're looking at the moon, you're not seeing it as it is right at that instant. You're actually seeing what the moon looked like a little over a second ago. And we can carry this logic out looking further away in space. For example, to the sun. So I'm sitting in front of a window, light from the window is shining in at me. The light that is shining through the window at me left the sun 8.5 minutes ago. So these photons or light particles that are coming in through my window started their journey around the time when Dan and I were setting up the Zoom call about 10 minutes ago. We can go even further out, outside of our solar system, and look at the nearest star to us other than the sun. That star is Alpha Centauri, circled here. It's a star that you can see from the southern hemisphere. And Alpha Centauri is 4.4 light years away. So that means when we look at Alpha Centauri, we're seeing it as it was over 4 years ago. And that's only the closest star to us. So thinking about these times also, for me, helps put in perspective the differences in length scale that we're talking about. So you can think about how many seconds are in 8 minutes. And that gives you information about how much further away the sun is from us than the moon is from us. And similarly, the fact that Alpha Centauri, it takes light 4 years to get from this other star to us, tells you how much further away this other star is compared to the sun, where the light travel time is only 8 minutes. So zooming out even further, we start thinking on galactic scales. So all of the stars we see in the sky are part of our galaxy, the Milky Way. And the Milky Way is very big. And to give you a sense of the scale, the light travel time between the center of the Milky Way to where our solar system is, which is on sort of one of the distant spiral arms of the disk of our spiral galaxy, which in the lower right here, this is an artist's illustration of where we live in the galaxy. The distance from us to the center of that galaxy is about 26,000 light years. So that means in the time that it takes light to travel from the center of the galaxy to us, or if you go back 26,000 years to think about what was happening on Earth then, that's around the time when pottery was invented during the Stone Age. So we're reaching back, not just to a couple of years ago, but to really back to the earlier times in human history. And these timescales get dramatically bigger when we want to leave the Milky Way. So this is a picture of the Andromeda galaxy, which is the nearest large galaxy to us, so sort of the Milky Way's nearest neighbor. That's a spiral galaxy, sort of similar to the Milky Way. And the Andromeda galaxy is 2.5 million light years away. So if you think about what was happening on Earth 2.5 million years ago, this is back to the time before Homo sapiens appeared. So as we step out away from our local astronomical neighborhood, we're looking back, or we're looking very far away, and we're also looking at what this galaxy looked like millions of years ago. And the Milky Way and the Andromeda galaxy are not the only galaxies in the universe. If we look out further, we can see hundreds of millions or even billions of other galaxies. So this is an image taken by the Hubble Space Telescope, pointed at an area, a patch of the sky, which looks pretty empty to the naked eye, an unremarkable patch of the sky that's a little bit smaller than the full moon. And the Hubble Space Telescope pointed at that area long enough to be able to detect light from very faint galaxies and to put this image together. And in this image, there are tens of thousands of galaxies. So most of these little speckles you see are not stars, they are other galaxies which are billions of light years away. And as I said, this is not a unique patch of sky. This applies, this sort of array of galaxies, distant galaxies, are something we can see, basically, something that we can see in every direction that we look. And just to put that into context, the galaxies in this picture, I don't know the exact time scale, but they're going to range from a couple billion years, seeing them as they were a couple billions of years ago, up to about, I think, if I remember the number correctly, about 10 billion years ago. So many of the galaxies in this picture, we're seeing what they looked like before the Earth even existed. And so these are the length and time scales that we're interested in when we're thinking about cosmology, when I'm talking about the very large scale properties of the universe. These are scales where we're not looking at necessarily the properties of any individual galaxy, but we're looking at sort of the distribution of them in a aggregate or statistical sense. And we're looking at the whole 14 billion year history of the universe. So as we in our universe here now, we look back out into space, we are looking back over cosmic time, over the history of the universe. And as we look far enough away, we're seeing the universe at different times. And because the universe has evolved over time, by looking back, we can gather information about those changes. So for example, there is a time when galaxies formed at some point. And so if we can look far enough back, we'll eventually no longer see any more galaxies as we look further away. And that'll be because we're accessing part of the universe that we're seeing at a time before galaxies appeared. And so you might ask, especially given the subtitle of this talk, what is the oldest thing we can observe? What's the farthest we can look? And that's going to be the main thrust of the rest of my talk. It's this thing that we call the cosmic microwave background. It's a source of light from the very early universe, when the universe looked much different than it did today. And I will be talking a lot more about where this earliest light comes from and how we can learn about physics from it. And that's going to be that's sort of the outline of the talk. But as I get into that, to give a little bit more context, when I say we can use the the cosmic microwave background, this oldest observable light, to learn about fundamental physics, what am I talking about? So I'm talking about big questions like, what is the universe made of, and what laws of physics have governed its evolution over time. And I'm going to give just an overview of sort of the picture of the universe, this description of what the universe is made of and how it's evolved over time, that as a community we have put together over several decades of different cosmological, different astronomical observations and theoretical developments. And a big part of this is this pie chart. So this pie chart describes the fractions of the mass and energy in the universe that's made up of different substances. And so I'll just walk us through it. The smallest piece of this pie, it's labeled atoms here, and this is 5% of the universe. And that 5% of the universe represents the the smallest slice of the pie represents the type of matter that we are familiar with on a fundamental level. So I've labeled it atoms. It's basically anything made of atoms, anything made of the constituent particles that make up atoms fits into this 5% slice of the mass and energy in the universe. So this includes us. This includes the computer that you're using to watch this talk. It includes the Earth. It includes the sun. It includes every star in every galaxy that we can look out and see. All of that is only 5% of the mass and energy in the universe. About a quarter of this pie, of the universe pie here, is made up of dark matter. Dark matter is a type of matter that interacts gravitationally, so interacts through gravity, but doesn't interact with light. So we have evidence for it existing, and some information about its properties based on how it influences visible matter that we can see. For example, the extra gravitational pull from dark matter influences the way that stars move in galaxies. And also, because dark matter feels gravitational attraction, it clumps into the structures. It clumps into structures over time. So and in those high density areas of dark matter clumping into structures is where galaxies form. So you maybe heard or could go and listen to some more information about this in Risa Wexler's talk that was an earlier talk in this series. The biggest piece of this pie chart is labeled dark energy. So this is about 70% of the mass and energy density in the universe. And in contrast to dark matter, which is clumpy and forms structures, dark energy, as far as we can tell, and we made a lot of constraints on this, doesn't clump up under the influence of gravity. Dark energy is, well, all of this is very mysterious, but perhaps even more mysterious. It's the name we give to whatever energy is driving the expansion of space to accelerate. And it has properties that could be consistent with just empty space having an intrinsic energy, but there are a lot of reasons why we don't think that that is the complete story. And the fact that we don't know we don't have a fundamental physics description for what dark energy is or for what dark matter is, means that a major takeaway or a major striking fact about this pie chart, this picture we have of the universe, is that we don't have a fundamental physics description for 95% of the mass and energy in the universe. We have a pretty good handle on this 5% that's made up of atoms, but dark matter and dark energy are really mysterious, and getting to have a more fundamental description of the physics behind these things, like what type of particle is dark matter, what is dark energy? These are some of the major open questions in astrophysics and physics today that we would like to work towards finding answers for. So dark matter and dark energy may be mysterious. We may not know a lot about them, but we don't know nothing. They couldn't be anything. As I said, we've collected evidence for their existence based on how they affect the visible matter that we can observe with our telescopes and how they've affected other measurable properties of the universe. So we can, for example, consider different descriptions of what dark energy could be and compare the predictions that we would get from those descriptions to our observations to sort of rule out things that dark energy may or may not be. And our hope in doing that is, as we narrow down the choices and constrain the properties of these mysterious pieces of our pie, we can learn about how to write these more fundamental descriptions for what they are. So that's a sort of context of like, what is the fundamental physics that we want to know about? The cosmic microwave background, which I am going to shift to talking about now, is one of the observables that we can use that provides a lot of information about these things and provides some of the key evidence, in addition to observations of galaxies and things, for indicating that dark matter and dark energy are these significant components of the mass and energy in the universe. So just pausing there for a second, I'm going to shift gears now to tell you about what the cosmic microwave background is. So like, where does this oldest light that we can observe come from? And then once I've talked a little bit about that, I'll shift to talking about how we get physics information out of it, how we can use it to test our descriptions of dark matter and dark energy. So I think as a starting point here, a good place to begin is to just break down the name cosmic microwave background. So cosmic means this is light that we observe from the cosmos. It's light we detect coming from outer space. And microwave refers to the fact that the wavelength of that light is in the microwave part of the electromagnetic spectrum. So this light is the same type of wave as the visible light that we can detect with our eyes. But instead of having a wavelength of around a micron or a millionth of a meter that visible light has, microwave light has a wavelength of a couple centimeters. So that's cosmic microwaves, microwave light coming from the sky. And background refers to the fact that we see this light coming from every direction on the sky in a very nearly uniform way. So in that sense, it's a background to any other observation we're making of the universe. So there's cosmic microwave background, that's what the name means, but what is it? And to understand where the cosmic microwave background comes from, and I'll probably start shifting a bit to saying, calling it the CMB. That's just the acronym for cosmic microwave background. This will be both for conciseness and out of habit. To understand the physics of where the CMB comes from, you need to know some cosmology. And the cosmology you need to know is on this slide. We need to know that the universe is expanding over time, and that as it's expanding, the universe is cooling. The stuff in it is cooling. So to think about the universe expanding, I've included this illustration of a balloon with galaxies on it blowing up. And when we talk about the universe expanding, it's not that the galaxy is getting bigger. You can kind of think of it as the average space between galaxies is increasing over time. And that's because space itself is stretching in the same way that the surface of this balloon that you can see marked with a grid is stretching as the balloon inflates. To understand why the universe would cool as it's expanding, we can use pretty similar physics to what we used to describe the relationship between the temperature, pressure, and volume of gases. For example, like the gas that might fill a balloon. So if you've ever used like an aerosol container, like one of those things that you blow air on your keyboard to try and clean it, or maybe spray paint or something, you might notice that the air coming out of the container is chilly, it's cold. And the reason that it's cold is you have this gas that was in a high density, high pressure state inside the can coming out to a lower pressure, lower density state. And that expansion causes it to cool down. And sort of in a similar way as the universe expands, it cools. All right, so if we follow the logic of the fact that the universe has expanded and cooled over time, that tells us that the universe at early times was much hotter and denser. And the time that's relevant for thinking about the creation of the CMB, the cosmic microwave background, is when the universe was younger than about 300,000 years old. So 300,000 years sounds like a really long time. But if you compare that to the universe's current age, which is about 14 billion years, 300,000 years is 1/46,000th of the universe's current age. So if you pull out your calculator and do the calculation, if you were 1/46,000th of your current age, you would only be a couple of hours old. So we're talking about a time that's really the infancy of the universe. And as I said, the universe is hotter and denser at this time. And in particular, the temperature of an average point in space in the universe at this time was around 3,000 Kelvin. or 5,000 degrees Fahrenheit. So for reference, that's roughly the temperature of the outer layers of the sun. So you can imagine that if the universe on average is the temperature that the sun is now, it's going to look a lot different from what it does at the present time. And an important way that the early universe was different is that it was ionized. So when temperatures are this hot, it's too hot for stable atoms to form. So in a cooler environment, if you have a positively charged proton and a negatively charged electron, because of electromagnetic attraction, those two particles are going to want to stick together and form an electrically neutral hydrogen atom. But when things are thousands of degrees, there are a bunch of very high energy light particles or photons flying around. And basically anytime a proton and an electron might try to stick together to form a hydrogen atom, they'll basically immediately get hit by a high energy photon, which will break them apart and prevent them from forming an atom. And so we say the universe is ionized, and that just means it's full of charged particles rather than neutral atoms. An important property of the ionized universe was that it was opaque. So light interacts very strongly with charged particles. And so if the universe is full of this soup of electrically charged particles, a photon or a beam of light trying to shine through space can't get very far without interacting with an electron, for example. And so instead of traveling in a straight line, like for example, when we look at the moon, that light bouncing off the surface of the moon travels in a straight line all the way to our eyes. The light in the early universe is bouncing around off of all of these charged particles. And that means that the universe is not see-through. So a way that I find helpful to think about this is you can think about why we can't see through fog. So we can't see through fog because light traveling through it will bounce off of water droplets in the air. And so instead of traveling in a straight line, it'll bounce around and scatter off of the water in the air. And so that means that you can't see very far because you can only see as far as the light is able to travel in a straight line. So in the early universe, the light's not bouncing off of water droplets, it's bouncing off of charged particles. But the result is the same. If you could travel back in time to when the universe was 300,000 years old and somehow through the wonders of your time travel technology avoid vaporization at 5,000 degrees, you wouldn't be able to see anything. The whole universe would be opaque, like you're in a fog, but it's a fog made of ionized light and protons and electrons. So the reason that the time of 300,000 years old in the universe is important or is significant is that this is a time when the universe, as it's expanding and cooling, first cools enough for those protons and electrons to stick together to form neutral hydrogen atoms. And this is a significant phase change in the universe. So you go from having light interacting very strongly with all of these charged particles to the universe being full of neutral hydrogen, and that light that was previously bouncing around can travel in a straight line. It's released from this soup of ionized particles. And it's that light that is released, that light can travel in a straight line, and much of it has been traveling in a straight line ever for the whole 14 billion year history of the universe. And that's what we observe today as the cosmic microwave background. So just to summarize, or to put a button on that, the cosmic microwave background is the light that we observe from when the universe first cooled enough to form stable atoms. And it's the oldest light that we can observe in the universe, because if we try to look past that time, about almost 14 billion years ago, or 14 billion light years away, I guess, the universe was opaque, and so we can't actually see through it. So we sort of see this you can kind of think of this, we look out and see this almost as a surface of, as if we were looking out into a fog. And we can make measurements of the properties of these cosmic microwave background photons using specialized instruments. So yeah, I guess, so now I'm transitioning from talking about where the CMB light comes from to talking a little bit about how we can gather some physics information from it. This picture in the lower right shows an artist rendition of the Planck satellite, which is a satellite that was detected or designed to make measurements of the cosmic microwave background. And it made the map that I'm showing on this slide. So when we measure, when we detect the cosmic microwave background photons with our specialized telescopes like the Planck satellite, we can use the property, we can measure their wavelengths and use the properties of the wavelengths of the photons coming from different directions on the sky to relate that to a temperature for that ionized, that early universe plasma, the charged particle photon soup that emitted that light. And what this map is showing is small variations in the temperature of the cosmic microwave background. So for the most part over the sky, the temperature of the CMB is remarkably uniform. But with the Planck satellite and other specialized instruments, we can detect variations in that temperature that are very small. So we're talking temperature fluctuations that are about 1 part in 10,000. And that's what this map is showing. It's showing a distribution of temperature fluctuations mapped out across the sky. So I think in this plot, the red points are showing spots on the sky that are slightly hotter than average, while the blue spots are slightly cooler than average. And it's a map of looking out at the sphere of the sky projected onto a 2D plot, just because it's kind of hard to show spheres on a slide. This projection works the same way as you would project a map of the Earth from a spherical globe onto a wall map like the one shown here in the lower left. All right, so these temperature fluctuations that we observe in the CMB are related to density fluctuations in the early universe. And they carry physics information based on what those density fluctuations were doing right around the time when the CMB light was released. And the properties of those density fluctuations are shaped by oscillations that were happening at early times. These oscillations, which I've tried to illustrate in this little cartoon, come from the fact that the universe is not completely uniform. So there are small density fluctuations. There are certain locations that have slightly more matter at them than average, and some locations that have slightly less matter at them than average. And you get fluctuations because, well, you get motion because of competing forces of gravity and pressure. So I'll start out by talking about the gravity. So gravity causes mass to attract mass. So you have a location that has a little bit more matter than average, there'll be more mass there. And that means gravity will draw matter from nearby places that have less matter into the overdensity. So the matter that's in the early universe and in the present universe is a mix of dark matter, the charged particles, and, well, yeah, the dark matter and these charged particles. So I mentioned earlier that dark matter interacts gravitationally, but not with light. So the dark matter I've tried to illustrate as these gray clouds in the cartoon. It'll clump up into the overdensity, and over time it'll become more clumpy as gravity pulls more and more dark matter into the overdensities. And at these early times, the charged particles are a different story. So charged particles interact with light, And so I'm talking about these fluctuations are happening in the time before the CMB was released. So we've got this soup of charged particles interacting strongly with photons. And that mix of electrons, protons, and photons will also fall into the overdensities under the influence of gravity. However, as that substance, the charged particles, the photons, fall in over gravity, gets compressed, and it will act as a gas. And if you've ever tried to squeeze a balloon, you know what happens if you try to compress a gas. The pressure goes up and you get an outward push. So as the charged particles and photons get pulled into the overdensity, the pressure builds up and eventually pushes outwards. And so you have, as I've tried to illustrate in my little animation here, the dark matter particles are just clumping up while the charged particles and photons are flowing in and out of the overdensity because of these pressure gravity oscillations. So when the universe cools and becomes neutral, that's when the CMB light is released. And so instead of interacting with these charged particles, the photons are able to free stream from wherever they were at that time. And so when we look at the map of the cosmic microwave background, like we would measure from the Planck satellite, we're seeing a snapshot of what these oscillations were doing when the universe became neutral. And if thinking about how you can get physics information from looking at oscillations in a 5,000 degrees ionized plasma isn't, if you're like me and this isn't super intuitive, it can help to build this understanding to think about some more familiar pressure waves, which are sound waves. So I'm going to take a little bit of a sidestep to talk about how we think about sound waves, and I'll then tie this back into talking about the cosmic microwave background. So I'm going to play a sound here, which hopefully will work. And Dan, let me know if this does not make a sound. All right, so what that was the sound of a guitar string being plucked, playing a G note. And if we think about what happens when we play that sound, the speakers of your computer are going to vibrate and bump the air molecules back and forth, causing a region of high pressure, which then the air molecules in that want to spread out. So they bump their neighbors, which bump their neighbors, and so on. And you get these waves of pressure fluctuations moving across the room until you detect them in your ear, or in this case, I detected with a microphone by the guitar. We can represent the fluctuations that are involved in these sound waves in a couple different ways. One way that's perhaps the most straightforward is by just making a plot of the amplitude of these pressure changes as a function of time. So that's what this green line here shows. Or for this specific guitar sound, I've made this plot of the amplitude versus time. So in this plot, the vertical axis shows how much the pressure is fluctuating at the microphone that I used to detect the sound. And on the horizontal axis, I'm showing the evolution of time. There's an alternative way you can represent sound waves that carries the same information, but lets you pick out different things a little bit more clearly. And that's by looking at the sound wave spectrum. So you'll notice in that amplitude versus time plot, there are different size wiggles. There's some bigger wiggles, sort of, and some littler wiggles on top of them. And these different wiggles correspond to sounds of different pitches or different frequencies. And so what the sound spectrum is, it's a plot of how much of the sound that you're hearing is made up of different pitches. So here, a high frequency corresponds to a high pitch sound, a low frequency corresponds to a low pitch sound. And if we look at the spectrum for this guitar sound, you can pick out a couple features. So there's a fundamental harmonic, and that corresponds to the frequency of this specific G note that the guitar is playing. You'll also see some overtones, which are multiples of that fundamental frequency. And then because I don't know what I'm doing with recording sound, you also see this triangle down here that's just like sort of crackle and noise of the imperfect sound recording. So on this next slide, I have plots. The top row show the same plots of this guitar note that I showed you on the previous slide, showing the amplitude versus time plot of the sound here, and also its frequency. And then on the bottom row, I have the similar plots for a violin being plucked to play the same note. So for a second, I'm going to have you listen to these two sounds. So first we'll play the guitar again. And then the violin. So these two instruments are playing the same note, but they don't sound the same. And the reason that they sound different has to do with the size, the shape of the instrument that's playing them, what it's made of, how a non-musician is trying to make them make a sound. And the way that those sound different to your ears is encoded in the different shapes of the spectrum. So you can see that because they're the same note, they both have a fundamental frequency, a peak at the same fundamental frequency. And they both have overtones, they both have some noise, but the relative height of the different overtones is different, as is their shapes. And that information encodes information about what the sound sounds like, and therefore about the properties of the instrument playing the sound. So if you can get maybe where I'm going, these pressure waves I was talking about from the early universe are sound waves in the early universe, and in the same way we can make a plot of their spectrum. It's a little bit different from the sound waves because instead of looking at fluctuations versus time, we're looking at fluctuations at different points on the sky. But you can kind of think of this as a similar way to this sort of cartoon that I showed of a sound wave, of like if you could take a snapshot of what the air molecules of your sound wave look like at a certain time across the room. The CMB fluctuations are a snapshot of what the matter in the early universe was doing under these pressure oscillations. And this plot on the right shows the spectrum measured from these CMB fluctuations at early times. And it looks a lot like the instrument sound waves. We have a fundamental frequency, we have some overtones. And in a similar way that the spectra from the guitar and the violin can tell us about the properties of those instruments, by looking at the relative peak and the shape of these spectrum peaks from the CMB, we can learn about the physics of the early universe. They depend, for example, on how much charged matter there is compared to dark matter. And we can make a prediction, given some description of dark matter and dark energy, for what that spectrum will look like. And by comparing that prediction against the measurement, we can test how well we are able to make that description. And before I move on, and I'll be wrapping up in just a minute, I wanted to play a sound which a professor at the University of Washington named John Kramer actually created so that we can listen to what the early universe sounded like. So the universe is very big, and so these frequencies were actually at much too low of a frequency. They're at much too low of a pitch for us to actually hear. So he's scaled up the frequency by a large factor so that we can hear it. And so let's listen to the early universe. So that is our echo of the early universe. So I'm basically almost done. I'm just going to give a slide or two that's kind of a teaser for future talks in this series. This is just to say, again, that given a model for our description of the universe on large scales, we can make predictions for what the CMB spectrum will look like and test it by comparing to measurements. And then we can also use that same model, the same ingredients, that pie chart describing what dark matter and dark energy, how much of them there is and how they behave. We can make predictions for how those tiny density fluctuations in the early universe will evolve under the influence of gravity over the history of the universe to eventually get us to the structure and the distribution of galaxies that we see today. And you can, through experiments like one that I work on called the Dark Energy Survey, I work on this with hundreds of collaborators from around the world. We can use telescopes to make maps of the distribution of galaxies in space, which gives us a distribution of matter in the late universe. So what did these small density fluctuations that we saw in the CMB turn into in the late universe? And in a similar way, we can also use our cosmological model to make predictions for what we expect those matter density fluctuations to look at. And so by comparing the measurements of matter distribution from galaxy surveys, like the Dark Energy Survey that I work on, and from measurements of the early universe through the cosmic microwave background, we can do a really powerful test on our ability to, given our model, to extrapolate to describe the evolution of the universe over its 14 billion year history. And I'll just note that in a couple, and I think sometime in August, Dr. Alex Amen will be telling you a lot more about the Dark Energy Survey and how it makes this matter map in the late universe. So with that, I'll close out my talk just with a quick summary. Things that I hope you'll take away is that the cosmic microwave background is a cool thing that we can observe, and it is light that's released when the universe first cooled enough to form atoms. And by measuring its properties, we can work towards answering some big open questions in the universe, like what is dark matter and what is dark energy? All right, that's the end of my talk. Thanks everyone for listening. And then I think, Dan, you'll take over now, right?
Yep, thank you very much, Jessie. What a fantastic talk. And thank you everyone for joining us. So we've got plenty of questions that have come in, but just a reminder that if you have any questions you still want to ask, we are still open receiving those questions. Either on YouTube, put your question in the chat, or on Zoom, head over to the Q&A button at the bottom of the screen. Or click on the link that I have put into the chat windows on both YouTube and Zoom, and you can send your questions in there. So the first question we had, so you talked about the Planck satellite and the measurements that that's made from the CMB. Has Planck sort of made, is that the state of the art, or do we have more to come with CMB experiments?
Yeah, so there's definitely more to come. So Planck is sort of the latest and greatest full sky survey measuring the CMB. So it's a satellite in space, so it can look out at the universe without the Earth getting in the way. And so it's sort of the end of the story, or like probably the best measurements we'll get on the very large scale properties of the CMB. But in terms of learning more about the smaller scale fluctuations, where there's a lot of physics information about different particles that make up the universe and the properties of dark matter, there are several ground-based CMB telescopes and collaborations working to make very precise measurements. So some of these include one called ACT, one called the South Pole Telescope. Coming in the future, there are several of these experiments on the horizon that are going to be really exciting developments. So there's more to see on the CMB.
Yes, there's a lot to look forward to then with CMB and learning about the early universe.
Exactly.
So on the topic of the cosmic microwave background, we had a question come in. So from the graph you showed of the peaks at the different frequencies of the cosmic microwave background, and how that's related to that image, those speckles. So the speckles look a little bit random. So how do you get from that speckle image to those peaks at specific notes, at specific frequencies?
Yeah, so let's see. So I find it useful to think back to that, the visualizations of the guitar sound as well. So if you remember, when you look at the sound wave over time, there's sort of some big wiggles with some little wiggles on top of it. And sort of the fundamental harmonic, the main peak, the the frequency that corresponds to the guitar note is related to sort of the size of those biggest wiggles in the sound wave and the sort of time scale of those. For the CMB, the peak in the spectrum corresponds to sort of a characteristic size of those speckles. So they're kind of random looking, but you could describe as sort of a scale on the sky where you see most of that fluctuation. And so that corresponds to the peak of the spectrum, or that sort of fundamental mode.
Yeah, it's almost like saying there's a sort of specific size of blob on that image that's sort of preferred to the others, that you see a little bit more commonly. So you talked about the CMB in terms of these sound waves, which sound like a classical phenomenon. Does quantum mechanics play an important role in the early universe?
Yeah, it does. So in the story that I was telling, starting from when the universe was about 300,000 years old, everything is basically classical at that point. But where the quantum mechanics comes in is asking, where do these small density fluctuations come from in the first place? And a piece of this picture we have to describe the large scale universe that I didn't touch on is part of this paradigm is the idea that during the very first tiny fraction of a second of the universe expanded at an incredibly rapid rate. And that idea is introduced to explain why the temperature of the CMB is so uniform across the sky. And something that comes for free along with this idea of very rapid expansion during the first fraction of the second is that that expansion would have to be so rapid that tiny quantum fluctuations on very small scale would get stretched out to macroscopic sizes. Okay. And once they're at macroscopic sizes, we can describe them classically without quantum mechanics. But we think our best guess, though this is another big open question in cosmology, is that quantum fluctuations are what seeded these tiny density fluctuations, which eventually grew under the influence of gravity to form galaxies and structure that we see in the universe today.
So quantum mechanics really did play an important role in growing the universe as we see it.
The plucking of the guitar string, if you'll.
Yeah. So going to this idea of then the universe expanding, will the universe keep on expanding forever? And what will happen if the universe does keep expanding forever? Yeah,
so exactly what happens in the future of the universe depends a lot on what the properties of dark energy are. If dark energy is sort of the simplest thing it could be, which is just some intrinsic energy to empty space, we can project forward how the expansion will look, and it will expand forever. In fact, it will expand and start expanding faster and faster and faster. And so and exactly how that occurs will depend a bit on the properties of dark energy, but sort of the most likely picture we have, given the information we've gathered to date about its properties, is that will happen. And eventually you won't, if future cosmologists are trying to look out into the universe will have expanded and stretched so much that you won't actually be able to see galaxies that aren't gravitationally bound to your own galaxy. And so you would have a lot less to work with. And so the universe in the future, and we're talking billions of years, will look very different than today.
And when the universe gets all stretched out and cold, does that mean we won't be able to form any new particles in it anymore? Will it just sort of go dark and run out?
I believe so. So experts on galaxies can probably speak to this more than me, but one of the things that will happen as things get stretched out is there's not going to be gas that can fall into galaxies, and to form new stars you need gas. And so as galaxies get more and more spread out, they sort of have all the stuff they've got to work with to create stars and shine. And so as stars reach the end of their life and explode, eventually the universe will get darker and darker. That's kind of depressing, but it's billions of years away.
Good. So let's go all the way to the other end of the universe then, when it's not cold and dark. The one question was, so if 3000 degrees is too hot for stable atoms to form, how can the sun, which is much hotter, contain helium and other elements?
Yeah, so when we talk about, so the sun is in fact mostly ionized, and people who know more about the sun than I do may correct me on some of this, but when we talk about the sun or other stars containing hydrogen or helium, we're usually talking about the atomic nuclei. So the sun containing hydrogen is mostly saying there's a bunch of protons in the sun, and if two hydrogen atoms, protons and neutrons stick together to form a helium nucleus, even if it has no electrons stuck to it to form a neutral atom, it will still have properties of helium. I'm certain I'm missing some things because I haven't studied the sun or stars in quite a while, but there will be some neutral atoms in parts of the star and the gas around it, and we can, I don't know, you might know more than me, Dan, on this.
Yeah, so the actual bits of the atom are still there, and it's just the electrons have come off the atom. And so actually one question we had on this, sort of a semantic question. So people have heard the term recombination in the early universe, talking about the electrons rejoining the nuclei of the atoms. But recombination implies that they were previously combined. So is that the case, or were they not?
They were not. So yeah, looking over the course of the history of the universe, this release of the CMB at 300,000 years is really the first time that neutral atoms form. The fact that it's called recombination, I think, is a bit of a historical quirk of the nomenclature of how it was discovered or initially described. But yeah, it doesn't really make sense.
One of those unfortunate words that I think somebody says at a conference once, and it sort of gets stuck, and scientists keep calling it that forever.
Yeah, I think basically.
Yeah. So are we able to say, so you showed the picture at the beginning of the expanding universe and sort of on the surface of a balloon, which is quite a nice graphic to expanding. But are we able to say anything about what shape our universe is?
Yeah, we can. And in fact, these fluctuations in the CMB provides a lot of information about that. So if you're thinking about like the geometry or the shape of the universe, a very simple question you can ask is, what do the angles of a triangle add up to? So in flat space, if you draw a triangle on a piece of paper, the sum of the angles of a triangle will always be 180 degrees. But if you draw a triangle on a surface of a balloon, and you can do this at home if you happen to have a protractor around, on the curved surface of a balloon, the angles of a triangle will add up to more than 180 degrees. And if you were very careful, and there's kind of another way of curving a surface, you can kind of picture like a Pringle chip or like a saddle. If you draw a triangle on that, those angles will actually add up to slightly less than 180 degrees. So by measuring the shapes of triangles, we can learn about the geometry of the surface they're drawn on. And with the cosmic microwave background, we were talking about this fundamental mode, this fundamental peak. And we can actually identify the length scale that corresponds to so that actually corresponds to the distance that light was able to travel between the beginning of the universe and when the CMB was created. And we can get a handle on how that length scale appears in the CMB by this characteristic size of these blobs. And we can look at what angle they take up on the sky. So that's like making one end of a triangle. And we can use that to check, do these angles add up to 180 degrees? And in fact, to pretty high precision, they do. So the universe, to our best understanding, obeys flat Euclidean geometry.
And it's pretty cool that we can measure that by looking at this ancient echo of the beginning of the universe too. Mm-hmm. So I think we've just got time for one more question. So what advancements in astrophysics are you most excited about in the next 10 years?
So though I think the cosmic microwave background is really cool, and I will be very excited to see how these upcoming CMB measurements constrain physics and the properties of fundamental particles. I mainly work on and spend most of my time thinking about galaxy surveys and how, on the end of trying to measure matter fluctuations in the late universe, how we can test different models of dark energy. And I'm excited for the Vera Rubin LSST survey, and I'm mixing up the acronym a little bit, but it's sort of like the next generation version of the Galaxy survey that I currently work on, which is the Dark Energy Survey. And LSST, this next generation survey, will be mapping the distribution matter across the whole sky to depths that we have not reached yet, and just mapping out these matter depths to these fluctuations over even larger volume of the universe. And by doing that, we'll be able, and especially comparing, this is a long-winded way of saying there are a lot of exciting experiments, both on the galaxy end and on the CMB end, that are coming up, and they'll both be able to provide, both of these categories will be able to provide really interesting and precise physics information on their own. But I think what I'm really excited for is seeing what we can do by combining those observables.
Yeah, so it sounds really exciting to see how much more value we can get by combining them than we can out of sort of the sum of the parts.
Exactly.
As it were. Well, thank you, Jessie. Thank you so much. And thank you, everyone, for joining us tonight. If you'd like to see Jessie's talk or any of our previous events again, they're all over on our YouTube channel. Just type kipac into the YouTube search box and you'll find us. And of course, don't forget to subscribe if you want to get updates. But for now, we'll be back in 2 weeks on Tuesday, July 28th, when Dr. Simon Birrer from Stanford will be talking about bending space and time. So that's definitely not one to miss. Find out more on our website at kipac.stanford.edu /discover. But bye-bye for now.